Hi everyone, thanks for coming out to hear us today. We are RethinkDB, an open source distributed database system. We are a relatively small company. We were founded a few years ago. And we've gone through a few iterations since we were first founded. But the latest release of the product, which we just open sourced on Friday, so it's been a crazy few days actually, getting lots of bug reports, things that as soon as you get all those eyeballs pop up. Should have been obvious earlier. But we just open sourced the system on Friday, so we're very excited to begin sharing it with the world. And in particular, in this release, we have a new query language that we developed internally that we think is pretty cool and we think solves certain kinds of problems. And that's what I'm going to focus a little bit on today. The theme of today's talk is actually performing simple data analysis inside the database using ReQL, our query language, the RethinkDB query language. Although we're going to have plenty of time to ask questions, so if this isn't interesting to you or you want to know about how all of this stuff is implemented, you want to know more information about the database and how it works, feel free to ask those questions afterwards. We're deliberately making this part short. We just started doing these demos, and so we don't really know what you're excited about and interested in learning about. So please feel free to direct this talk as you will. And I might not be able to answer all of your questions, but fortunately we brought along our fabulous founder, Slava Akhmachet, who will be able to answer any question you have, and not just about RethinkDB, about Lisp, life, the universe, and everything. So, without further ado, I think I'm just going to jump into the demo itself so you can see what it's like to program against RethinkDB and how you can use RethinkDB, nothing more, to do simple data analysis. I've got friends at other startups who they've got a simple NoSQL database that they're using, but they can't do anything more complex than gets. And so they end up having to bolt on a really heavyweight query analysis system on top of it that just causes all sorts of headaches. So we think that one of the areas that we're particularly strong is in this small-scale data analysis task that can happen directly inside the database itself. So I'm actually going to switch windows now. These are my only slides, so yeah, you've been saved from that. And we're going to switch to our web UI. So this is obviously just a web browser. We're connected to a RethinkDB node that's just running on my machine here. And even if this were a large cluster of RethinkDB nodes, we could connect to any one of our nodes and bring up the same UI. And from this interface, we can control the entire cluster. We deliberately focused on making RethinkDB clusters easy to use, easy to administer. So we look at some of these tabs here. We've got a dashboard that shows us any issues that come up. Maybe a machine has gone down. We can view performance graphs, these kinds of things. We can see what tables we have in our database. But what we're going to use today, in particular, is the Data Explorer. This is designed to allow the database administrator to run simple queries against the database to see the data that's in there. But this Data Explorer actually embeds the JavaScript driver that we built for you to embed into your JavaScript applications, in particular your Node applications. So this is actually the full JavaScript driver embedded directly into the Data Explorer. So the query that we're going to type today is actually identical to the kind of thing you would do inside of your Node application. It's no less powerful. And as for what kind of data analysis we're going to do today, well, there's been lots of talk in the last week or so about exit polls and who voted for whom and stuff. So we thought, well, we'll use some polling data and see if we can come to any meaningful conclusions by doing analysis of the polling data. So in particular, we have some polling data from earlier this summer. So if we do a little bit of retrospective, looking at this polling data, maybe where are we going to invest in order to get the most bang for our buck, electorally speaking? So in particular, we're going to focus on states that, as of sometime in June, whenever we got these polls, states that were slightly Democratic leaning but were well within reach for the Republican candidate. So let's just pretend, excuse me? This data set is relatively small. We have 2 data sets. One is polling data for all 50 states and the District of Columbia. And the other set of data is population statistics for all the census-designated places in the US. OK, so our task today, let's just say our friend Alice has asked us to help her friend Carl decide where he's going to invest his PAC money to get the best bang for the buck. So we're just going to start off with a very simple query. And I'm just going to copy it so I don't make any typos. So this is a very simple query. We're looking at our table of polling data. And it's actually, it's a fairly complex table. So if we just look at the table itself, I'm just going to comment out these lines so we can see what the data looks like in this table. Let's see, we've got a lot of these unnamed fields. We need to clean up the data a little bit. So we're just going to get we're just going to get the columns that we're interested in. OK, so here we now see our states, the latest poll data. So Alaska has 3 electoral votes. The GOP candidate was ahead 62 points to 38 points. So Alaska is not really what we're interested in. Our candidate's going to win that one handily. So really what we want to do is we're going to go back up to our query. We're going to look at states that we don't have yet but are close. So you see this filter, it takes an anonymous JavaScript function. And what we're doing is we're filtering these rows by rows where the Democratic candidate is leading the GOP candidate, and the difference between the two is less than 4 points, so within reach. And here we get 3 results: Florida, Nevada, and Virginia. Now this is a diverse set of states. Some are large, some are small. This isn't quite enough information to make our investment decision, because obviously we're going to have to convince a lot more voters in Florida than we would in Nevada, even though the margin of difference is smaller in Florida. So this is where our population data is going to come in. So we'll come back to this polling data later. But let's go get some population data so we can make better sense of our chances here. All right, so I'm going to comment out these lines again just so we can get a feel for what our data set looks like. OK. So this is just census data from the 2010 census. You can see we got a lot of stuff in here. Deaths in 2010, estimated base 2010 population. So most of this we don't care about. So again, we're going to filter out just the rows that we want. So we're going to pluck our population estimate for 2011, the city name, or in most cases actually county names, or I guess CTY probably stands for county, and then the state name. So we clean up our data a little bit. We can see we have population data for various counties. Now, of course, this isn't in quite the right format, because what we really want is state-level population data, because our polling data is at the state level, not the county level. So we're going to run a group by on the state name, and we're going to have it sum the populations across those groups. This population estimate 2011. Oops.
So what is R?
What is R? OK. R is just our top-level namespace. So in your Node application, you'd probably import RethinkDB by including a line, something like var r equals require RethinkDB. And we've tried to keep this consistent across all of our different language drivers. So it's obviously not quite the same because there's some language differences. But in the Python driver, for example, you might import RethinkDB by saying import RethinkDB as R. And that will help keep the naming of the API functions consistent across the various languages. So all of these are similarly developed. The RDB query language is developed as a domain-specific language embedded within the host language. So even though it's all the same API names and everything, the syntax is deliberately designed to integrate itself into the host language. One of the things that we think we've all had difficulty with with writing SQL queries is we end up doing a lot of string concatenation and interpolation, and we're trying to construct this complex query structure with these flat string operations, and that gets us into trouble, like SQL injection and stuff. So we really wanted to focus on the developer experience, embedding the RethinkDB query language directly into the host language like this.
What is the magic that allows where you have r.sum?
Yeah.
What's the magic that knows that that is now within the context of the table that we selected earlier?
Okay, so this group by is actually syntactic sugar for a group MapReduce operation, and that would be a little bit. It's just longer to type out for a query that we already have a shortcut for. This r.sum is just a shortcut for a common reduction, which would be sum the field pop estimate 2011.
So we're just it's not that it's referring to anything in the actual table. It's just that whatever the column is at this point in the operation that's called pop estimate 2011, use that.
Yeah.
Okay. That makes sense.
So if we had done the full group MapReduce, you saw earlier we had the anonymous function for the filter, and we're not actually passing the JavaScript function itself. What we're doing is providing that syntax as the variable that's passed. So we only actually call that function once, and the variable that's passed in is a symbolic representation of the current row for that operation. So in the filter, the doc in the function argument list is the current row, and then we chain operations off of the current row. We'll see another example of this. And group MapReduce is implemented the same way, where you have a grouping function, a mapping function, and then a reduction function. And group by is just a shortcut syntax for common reductions like this one. So we'll see another example of this.
You probably have defined all these operations, and is that what it is?
Yeah, so we have r.sum is just a common operation that we've chosen to predefine. And we also have an average function and a count function. So.
Are these?
Actually,
it's easy.
I know it is. Somehow it missed the release.
Yeah, we can always add more, and of course you can define them yourself. The r.sum actually just returns an object that contains a mapping field, a reduction field, and I guess grouping field.
Is there an optimization layer that will take? So you can say that this entire thing is effectively a declarative statement of your query. Do you have an optimizing layer that takes that declarative thing, potentially manipulates it, and then creates a chain of MapReduce or other jobs to run against the data? Or is it basically run literally the way you?
I think the operation that is run is pretty close to literally what this looks like, although there is a significant transformation that occurs. So this query will actually, from here, gets compiled to a protobuf. So it's serialized into a protobuf representation of the query syntax. That's sent to the node that we're communicating with currently. And then that node is responsible for coordinating the execution of the query. And that will identify which nodes in the cluster have the data that we're looking for. It will then construct another representation of the query for each node that we call a transform stack. Oops. And then send that to each of the nodes that are participating in the query. And then those nodes will send back the result, and then it will do the aggregation operations on the node before sending the data back to us. And I don't know if we do any particular optimization steps.
The optimization question. So the thing, you're right in the sense that this was designed to be both declarative, but also it has operational semantics. So you could execute it literally, or you could treat it as a declarative program. And there is a little bit of transformation that we do, but the optimizer is pretty immature, I think, in the sense that it does like the obvious things, right, that you would expect. But when you get into complicated cases, it could certainly be improved significantly.
Okay.
Okay. Any other questions at this point?
So, for instance, the pluck is an important optimization.
So the pluck is optimized.
Yeah.
Like you're not gonna, when you do a pluck and you're getting data from multiple nodes, you're only you're like cutting out
But
stuff
if
that
I
doesn't
failed
matter.
to do the pluck here, that might actually have ramifications for the job underneath. Like you could, like you're not going to synthesize the pluck based on what I choose.
Oh, I
to.
see. So yes, this particular optimization we don't do.
Okay.
The language was designed with that in mind. But
I get it, you know, and it's an early stage, right?
Yeah, yeah.
So yeah, that's totally cool.
Yeah. So the last line in this particular query, all this does actually is a rename. That's just going to be convenient for what we're going to do next. So all it does is rename the state and population columns to state and population. OK, so now we have our population aggregation statistics. And really what we want, now we need to somehow join that data with the polling data together. But most NoSQL databases don't support joins, so are we out of luck? No, fortunately, RethinkDB supports joins. All right. OK, so I'm gonna go back, and this is going to be a big-looking query, but we're going to go through it step by step, just so I don't have to type it all out again and make some mistakes. OK. So this is, again, what we had here. Same thing we just saw. We're doing the group by, and then we're just renaming these columns. But now we're going to do a join with our poll table, which we were looking at earlier, on the state field. And so the equa_join is an optimized join that will end up only looping through the left-hand table once. So this is not a full n-squared join, although we do support other kinds of joins. In this example, we only need to do this simpler kind of join. And so let's start just by looking at the output of the join, and we'll get rid of these other lines and then go through those. All right, so the first thing you notice is we have actually grouped them into left and right subfields. And what's nice about having a JSON document store is that we can have these nestings of our documents. And if we expand these, we can see these are just the same data we were looking at before. Here's our polling data, and here's the population data that we just constructed. So we're just going to zip that. All this is designed to do is to merge the left and right, which we can go ahead and do there, because none of the fields are going to conflict with each other. And then we're going to, again, do a pluck to get rid of all the stuff that we don't need. So in this case, we're just looking at the state, its population, its number of electoral votes, and these voting or poll percentages that we had earlier. All right, so now we've successfully added our population data to essentially the data we were looking at before. And then we're going to apply the same filter we had before, which you recall helped us identify the states that our friend Carl is interested in, which again are Florida, Nevada, and Virginia, now with our population data that we wanted to find. OK.
Sorry,
yes?
How would the equa_join impact performance? I mean, the reason why the other NoSQL that what join is for performance purpose. How about this one?
So this particular join actually is doing an optimization where for each row in the left table, it's doing a index lookup on the right table. So in this case, we were able to do this because the field that we're getting our foreign key from, the state, is actually our primary key in this table polls. And so that allows us to very efficiently look up data from the other table. So it's linear in the size of the left-hand table, and I guess logarithmic if you think about the index in the right table. But we also support a full inner join, which would do an n-squared operation, or an n by m.
If the table is sit in the separate cluster, how would that?
Right. So in this case, we're only running one node, so all this data is on the same node. But in the case where we had a large cluster, one table was, say, spread out across a few nodes, and the other table was spread out across a different set of nodes. What we'd end up doing actually is sending this query to all of the nodes that have data from the left-hand table. And then each of those nodes is going to then stream the data from the right-hand table and then implement the join on that node and then send the full result back to the aggregation step on the sort of coordinating node.
Join will occur on the single
No, it's spread out across all of the nodes that have data in the left-hand table. So this is one feature we like to try and emphasize about RethinkDB is these queries are as distributed as we can make them. So if our left-hand table, our county data is spread out across some number of shards, each one of those shards will process its portion of the query in parallel to the other shards. So depending upon how your data is distributed across your cluster and depending upon your query, you can get a lot of parallelization out of the running of the query.
So the aggregation happens back on the coordinator node, though it's not distributed?
So in this case, it will, because we need to gather all of the data from all the nodes first. But if a particular subquery could happen on, so anything that can happen on the lowest level node will happen on the lowest level node. So if we were doing some extra filters and stuff on the results of the join before sending it off to be joined with some other data, those filters will be applied at the lower level first. And all of the query evaluation is lazy as well. So if we had millions of results, the client would have to request more results before the cluster would bother computing more results. OK, so now we have the data we're looking for, except we're trying to compute a return on investment here. So what we really want to know, say, is how many votes do we need to win in each of these states in order to win the state? So we're going to do that by multiplying our population by the difference between our polling numbers. So we're going to have to do a little bit more math. And I'm just going to grab that here. OK. OK, and let's see. OK, so what this is doing is, again, here's this, this anonymous function. So this is a representation of the current row that we're then going to chain our operations off of. And so this function is for each one of these rows here going to first find the difference in the poll numbers, divided by 100, of course, because these are percentages. And then it's going to multiply by the population for that state in order to find the number of votes that we need to win that state in order to move it into the red column. And then we're just going to also pass along the name of the state. So if we run this query, we see that we would need, let's see. Actually, you know what we really need? We want to know what gives us the best bang for a buck. So we're just going to order this data. Order by votes. OK. OK, so now we see that Nevada actually seems to return us the best bang for the buck, mostly because it has the smallest population. Of course, though, this is the US Constitution we're talking about. It's not voters who matters, it's electors who matter. So really what we want to know is the Electoral College numbers. So we're going to, again, divide this data by the number of Electoral College votes for that state so we can compute the number of votes per Electoral College vote that we need to convince. So we're going to divide this by EV, or doc EV. And then we're going to, again, order by votes. And once we do that, we find that because Florida also has a greater number of votes, Florida gives us the best bang for our buck with 13,000 voters per Electoral College vote needed to win the state. And that's the number we're looking for. So that's the end of my demo. Does anybody have any more questions about how this works? Yeah?
So I think, the language, query language is a little bit tech-oriented, not the business people-oriented. So are you guys planning to have some tools on top of it to easily write this kind of report?
Ooh, I don't know of any plans to solve it. Were you thinking?
I could probably answer that. So every time we show this to people, everyone's very interested in a SQL front end on top of it. right? So business people that know SQL could
makes
write SQL. And from our perspective, I mean, we support multiple protocols already, so SQL would be pretty easy to write. But it's really a question more of sort of business priorities and who do you go after first. Because business people, in terms of buying systems like this, are not necessarily early adopters. So like the moment we actually get demand for it, it will be pretty easy to add.
Yeah.
So your demo was focused towards the analytical approach, right? Analytical questions. So is your current focus on analytical use cases, targeting columnar, like competing with columnar data, analytical columnar databases, or are you more geared towards like transactional databases, key value lookups, or MongoDB, or something like that? Or does it do both well? It just needs to be configured one way or the another based on the use case.
So we're not currently focusing on the analytics use case. The point of this demo was just to demonstrate something cool. We could talk about lots of other features of the database. It's not going to compete with a columnar data store on performance because it is row-based. But if you are writing, our target users for now are people who are writing web applications, and they need to store their data somewhere. And they might also need to do some aggregation of their data. They've got a diverse set of needs, and they spend a lot of time, and they end up spending a lot of time configuring large stacks of analytic engines on top of their database and all of this stuff. And the point of my demo here was just to show that you don't really need all that stuff. Your database should be able to do that too. And whereas we wouldn't recommend RethinkDB for really performance-sensitive, big data analysis tasks, we think that ReQL is perfectly good for a small-scale task like this, something that might come up in the course of serving your web application, that you don't need to attach this big analytics stack on top of your database.
So the target customer, target data to store in the RethinkDB, so kind of smaller data or it's a big data, it's a target scenario for customer behavior.
So in terms of bigness of data, we've tested RethinkDB on clusters of up to about 16 nodes. So we haven't really tested beyond there. I don't think we would recommend trying to test it beyond there. We have not tried to optimize the scaling there at all. But we think there are a lot of small teams, a lot of startups, a lot of web applications that probably don't need more than 16 database nodes to serve their application. And so small to medium-sized projects probably.
16 nodes with how much data on them?
Well, I guess as much as fits on the node. The servers that we've been running on around 80 gigabytes of memory. However much RAM your machines can support.
So is this entirely memory?
That was
Sorry. First question.
Last time I read anything about RethinkDB was focusing on solid state.
Okay, so no, it's still okay. That serializer is still there. It's not all in memory. However big a disk you want, we can write to it. But the performance is going to end up being constrained by how much RAM you have to run your queries in. If you're doing a big join and it doesn't fit in 80 gigabytes, you're sort of screwed no matter what you're doing. But yes, RethinkDB or at least ReQL, is built on top of an earlier serializer that we built that was optimized for solid state performance, although it does just fine on rotational disks as well. So all of that is still there, and we still have good performance, read-write performance on disk. But your performance for these kinds of analytic tasks is going to be dominated by if your data set fits in memory or not. So,
I guess I need a little more context. What is the motivation behind RethinkDB and ReQL? Why does it exist, or why does it need to exist given the other NoSQL choices out there? What is it that's unique about this? What's it bringing to the
So it's probably one of the more common questions that we get. When we released on Friday, the #1 comment on the Hacker News post was just, help, can you just give me the like 5-line marketing summary of why this is better than Mongo? And let's see, I suppose the answer to many, Slav, you probably could answer this better than I could.
Yeah, so the way we sort of thought about it is we talked to an enormous number of people that put these NoSQL solutions in their infrastructures for various reasons. And the sort of consensus that you get around the industry is that it's relatively easy in the sense that it's easier than scaling like relational systems, but it's still pretty hard. So the teams that manage these systems operationally and then developers, engineers that build applications around them are still pretty big, and it's still a big sort of chunk of development time. And people sort of accept the fact that these things are hard and they take time and they take effort. And when we look at this, we realize like, hey, this scaling to 16 nodes doesn't have to be hard. There is no reason for it to be very, very difficult. So we built ReQL because we thought we could build a development environment that really, really makes people's lives much easier than it is today. And we built a lot of operational tools. I don't know, Bill, if you want to show how like replication
Sure.
and sharding works, but we thought like to shard your data to 4 machines, you literally should be able to click a button, hit shard, and just make it work. And no solution today does it like that. I mean, it still takes hours and hours to set up, whereas with RethinkDB, it literally takes 5 seconds to get started, reshard, and query language is beautiful, easy to learn, very, very simple. And it resonated really well with an enormous number of people.
So then can I take it that the sort of sweet spot is where you're saying, I'm building an application, I need a data store behind me, and it should be super easy to use as long as I don't need tremendous scale. And that you're kind of optimizing for that use case, as opposed to competitors which are saying, well, we're tackling enormous scale, but that means that there's this massive upfront cost of maintaining the cluster. Is that what you're saying, basically?
So what we've built is the architecture inside fundamentally was sort of designed to scale to very large clusters. Mm-hmm. But there's a lot of engineering work that has to go into it to actually make it happen because there are bottlenecks here and there, and it sort of involves effort. And we decided to focus on developers first and the user experience first, because we thought that's where the market is lacking most, right? Because there are pretty good, scalability solutions out there. Like Hadoop is pretty phenomenal. So we did this first. We did the development environment first, and that's the sweet spot right now. And what we thought is, whenever when we polish the development environment and we polish the language and we polish all of these things, we're going to move on to removing the scaling bottlenecks next. And at that point, you're going to get a very usable system that can also scale to a massive number of nodes. So there's nothing fundamental that prevents us from doing that other than the fact that it's work, right? And it's probably going to take another year or 18 months to get to the point where you can scale above 16 nodes, just purely because there's other work that's more valuable to do right now.
So the architecture is yours, like the whole synchronization between nodes and distributing the work is your infrastructure you built it?
The whole thing is built from scratch. All the IP is ours.
Using MPI or anything?
No, we use C++ and we built native sort of just serialization algorithms and things like that. Yeah. So you're running one node, right?
I'm currently only running one node, so
okay. If we run more nodes, we could show you. But basically, what happens is when a node fails, you just get a nice little red box that pops up, and then you say, declare this node dead, and then the whole cluster just keeps running. It was just made to be super, super easy for administrators. So, like, if you get a pager going off at 3 a.m., like you don't curse too much.
So is the communication only done through one node that then distributes it to the other node?
No, it's all peer-to-peer.
Oh, it's all peer-to-peer. It's
Okay.
like semantic also.
Cool.
Yeah, completely.
So
So
it's
like,
not master-slave.
it's master-slave underneath, in the sense that you can have multiple masters and multiple slaves. So if you have a table, you have 4 shards, you have four masters for that table, a master per shard, and then you have replicas. But they all communicate peer-to-peer. So what happens is a write always goes through the master, and up-to-date read also goes through the master for that shard, and out-of-date reads can go, anywhere. But you can route through any node, and there is no single point of failure.
And that also means, of course, that when you are connecting from your application, or you're connecting like we are through the web UI, you can connect to any node in the cluster, and you have the same tools. It doesn't actually matter what node you're talking to. So if you lose a node, just connect to another one.
Just create a bit for your nodes, and you're good to go.
So how does it? Oh, sorry. So my question is, how does it work with the streaming data? For example, suppose I have the streaming data coming in, and I want to calculate analytics on top of it. So will it scale, like will the writes and the reads scale on the? So for example, so I have a website.
Yeah.
And people are writing logs, right? So I'm writing logs for that website, for example. And that's just, I want to stream it to that this DB, and I want to calculate some real-time statistics. Will it work?
I'll probably stand up. So yes, so the thing was built with MVCC. There's multi-version concurrency control throughout the whole system. And the motivation for that was like when people run MongoDB, what happens is they're having their real-time system, and then they want to run a long query, and the whole thing locks up. So what we did is we built this whole copy and write infrastructure, and then what happens is if you run analytics queries like the ones Bill just showed you, and you have real-time data coming in, the queries will still run. And there are all sorts of questions we can get into about consistency guarantees and stuff like that. We provide per document consistency right now and slightly stronger guarantees in some other cases. But your system won't lock up, and in fact, if you have replicas and you report you're okay with out-of-date data, you can route your real-time stuff one way and analytics stuff another way, and everything will work just fine.
And how big data can you hold? Like 16 nodes, how much data can you hold?
So it depends on what you're doing. Like if you're doing a lot of random access, you're pretty much limited by RAM, as Bill said. If you're doing sequential things, you can do stuff on disk, and you'll be fine. So for example, like aggregation, right? If you're doing group by, you don't really need random access. That means you can put a terabyte of data in each node and just run it, and it's going to work perfectly well. If you're doing random access, then and you're having a rotational disk, then you're just going to be killed by disk performance, just like any other system.
So if I had to use this for analytical database after a ETL that's done, does it support any kind of concurrent load? Say my 600 node Hadoop cluster just finished a bad job, and I need to load the ETL data into this. Does it support any Hadoop connectors or parallel loading mechanisms, or what kind of throughput write can it support?
We didn't do any Hadoop connectors yet. There's sort of all sorts of tools to be built around this, right? Connectors to other languages. Right now we do Python, JavaScript, and Ruby.
Does it do parallel loading?
How do you mean?
Parallel loading, say I have the output is 2 gigs file, and I split it up.
Yeah, that will work fine. So you can, like, if you have a table here, you can split it into 16 shards. And if you have a 16 node cluster, you're going to have a shard per node. And then you can just split, your loading and send data to each node, and it will route everything just fine, and it will parallelize it completely. So that will work, but there are no Hadoop connectors, so you sort of have to write that yourself. And we'll probably provide tools pretty soon.
The connector part is kind of simpler, but
right.
The parallel loading mechanism is one of them.
Yeah, all of that will work.
You talked about lazy computation.
Yes.
Was that, so is there pagination involved? Like, does the user give you quota and you get the next set of results, or is it just a limit on I want these results and then you
So the client, yes, the question is about lazy computation and pagination on the client side. So the clients are configured to I guess the clients in conjunction with the server are configured to chunk the data into sets of about 1,000 results right now. And it's up to the client to request more data before the server will produce more data. So actually, the way that this data explorer is designed, we only had a few results to look at. Well, I guess they're gone now, but we only had 3 states to look at. But if we had a much bigger data set, and we ran a query to grab the entire many millions of lines table, we'd only get the first 1,000, and then we could page through it, and then the client would automatically request the next batch when we had gotten through the first 1,000 results. Yeah.
When the map happens, you already have all the results. You have the results set, complete results set.
So which map?
You do, like you had 2 tables, you do a join.
Yeah.
Each one you have like say 5 million rows there, and then you get the first 1,000 back. And now I need the second 1,000 back. So does the map, does that
join operation happen again and using the limits on them, or how does that work?
Okay, so the computation sort of remains in a state of progress until the client explicitly tells the cluster to kill the computation. So the server has the data set still in memory waiting for the client to request the next batch. And for a complex chain of commands, it could be the case that the server has already retrieved the first 10,000 rows from the join, but has not yet computed the rest of the join, and already done a map step and a filter step, and is waiting for data to sort of get pulled out of the queue before it bothers to pull more data into the queue at the other end of the computation. So if we were to do a gigantic join and a filter and then only request the first 1,000 results before killing the query, most of the join would not end up being computed at all, because it was waiting for the client to request more data before it bothered to compute more.
I'll go again.
Yeah.
Do you happen to have any high-level architectural slides that you can share in the last few minutes?
I don't have any slides, but we can talk.
Draw something.
We can draw something, yeah.
Like reads and writes, how do they happen? Where does data get stored, cached, computation?
That's a long, long, long conversation.
That's why I said high-level pictures.
Yeah. I mean, I guess. Well, as Slav was saying earlier, for every shard, so you can actually, on this screen, you can configure your shards for the table. So we can both here tell it how many replicas we want, and here we can tell it how many shards we want, where to divide the shards. We can also tell it to automatically find shard boundaries for us. And those will then get distributed across multiple nodes. And in order to get any data in that shard, we go to the master for that shard. If we want to write any data, we go to the master for that shard. If we specify that we're OK with out-of-date reads, then we'll go ahead and route it to any replica. So you can get better read performance if you specify that you're OK with out-of-date reads. And furthermore, underneath the shards that you set up here, we'll set up hash shards underneath that will divide the shard across multiple cores on the same machine. And so if we do a big read to a table that happens to only be on one node, say there's only one shard here, but underneath there are some number of hash shards that we've defined that allow us to parallelize the query on that node on multiple processors. And the query will always get pushed down to the lowest node possible. So so here we do a filter on some table. The filter operation itself gets sent to each shard, and the filter is performed on each shard for the table before the results are streamed back to the client. So all of that happens in parallel. Yeah.
So can you describe the ways in which you have tested, not the query part of it, but like the DB store part of it? So how do I trust that it's going to work exactly?
Right. So the question is about testing of the underlying data store. Can we trust something that was written from scratch if it hasn't been tested? Well, RethinkDB has actually been in development for 3 years. The query language is fairly young, but the underlying data store has actually been around for a long time. And so before we developed our own query language, gosh, we went through a phase where we thought we were going to be a MySQL data store. Went through another phase where we thought we were going to support memcached. But the underlying serializer has been the same. So actually a lot of testing has gone into that part of the database. And a lot of performance testing early on. We were very focused on demonstrating that our serializer was fast. So do you know anything more about the testing?
Yeah, I mean, the test infrastructure basically runs every night. It's actually distributed. It used to be distributed in EC2, and then it got too expensive, so we bought a bunch of machines, and we run them in the lab. So we run nightly tests. The longest one runs for a couple of hours. The shortest one is, a couple of seconds. And there's just an enormous number of tests, concurrency tests, things like that. But I mean, if I were completely honest, I think if you're putting really, really critical data in here, I would wait a little bit until early adopters vet this out and other people look at the code, build more tests, things like that.
Have you tested things like packet drops, packet duplications, and things like that across multiple nodes?
Yeah, we have. There are some tests written on top of like a network virtualization layer, because there are software packages that do that, right? That will just sort of do all sorts of interesting things with the network, and we have these mock layers that will do things with the network, with the disk, all sorts of component, in between. But it's still pretty much impossible to test all of the cases. I mean, the combinatoric explosion of cases is enormous. So I would bet, like, a huge number.
It's infinite.
Right.
But what was the motivation to start in this project when you start with infrastructure? What was the motivation? It wasn't the language because it's new.
Yeah.
Mm-hmm.
You started 3 years ago. What was the motivation?
Well, so when I started this, I was a PhD student in Stony Brook University over on the East Coast, and we were doing mammalian brain simulation on IBM Blue Gene supercomputers. So these were basically like regular computers with really, really fast networks and really, really fast disks. So we were doing that, and Stony Brook was the sort of low-energy place. And we thought, okay, we know all this stuff. We looked at the industry, and there were very, very interesting things happening with data. How people access data, what they do is just everything was changing, commodity hardware, sort of virtualization, all stuff like that. And we thought we didn't know exactly what's there, but we knew that there's something there. And we just moved out here, we raised some money, and we started building out the infrastructure. And while we were building the technology, we sort of internally just got better and better and better at building products as opposed to technology. Right, and over time, I think it took like 3 years to get to this point where we sort of got the technology there and we sort of got the product sense to build something meaningful for a lot of people. But I think the original motivation was just to build something cool, really.
So it always.
You're on the right track.
Do you support range queries and secondary indexes that in pipeline? So currently it's just primary indexes, right?
So we do support range queries, but only primary indices.
And is secondary indexes also a feature? Or?
Not currently, although that's definitely on the feature list. It's been one of our most requested features. It's just a question of prioritizing things. Got a lot of feature requests currently. So.
Secondary indexes, especially when if you're going to be distributing this thing, is that even it's going to be a scatter gather at that point in time because you would be distributing your data as per your primary indexes.
Mm-hmm.
And then having global are you thinking about global secondary indexes or just in that partition?
He knows more about what our plans are than I do. How are we going to do this?
Secondary indices. So the thing is, in a distributed system, to get the secondary indices right and to make them good and like seamless is very, very difficult. So there are other products that support this kind of stuff, but when you actually look at how people are using it, you find they're either slow or they don't do quite what you expect, or they're hard to set up. Like there are all these issues. And one of the sort of design decisions we made about this is we're not going to put anything in unless we figure out exactly how to scale it, how to make it easy to use, and how to make it just like a seamless user experience. So we sort of know how we're going to do that technically, but there's a lot of engineering work involved, and there's like UI work to make all of that happen. So I think secondary indices realistically will probably happen 6 to 8 months from now. I doubt very much it would happen earlier.
We had another question somewhere.
So it's MVCC, so that means that you're doing some kind of compaction, Postgres vacuum, right? I assume that with high write volumes, you're going to run into issues there. I was wondering if you're dealing with that in some novel way, or.
Yeah, so the garbage collector, I mean, that part was written a while ago, and basically it's a concurrent incremental garbage collector. So it's not like vacuum where you have to stall the whole thing for like a minute while you clean up. It happens completely concurrently with like writes, and it happens incrementally. So if you actually run a write workload and you turn on logging for the garbage collector, you'll see all these log messages, but it won't really impact the throughput of the system. Especially if you're running, so on a rotational disk, it's harder because you're jumping around reading. But on an SSD, it works. I mean, you maybe lose 10% of write throughput while collection happens. But you never stall. like at all. And the garbage collector is probably like, at least it's not something visible, right? You can show a pretty UI, but technically it's probably one of the most interesting things there, other than the query distribution and how we do the pushing of the queries down to node.
And related to that, you know, resharding, especially of the indices and that sort of stuff. I'm assuming that you're doing something to handle that. I mean, it might go hand in hand with the garbage collection, or it might be. And you know, in particular, you know, when you're doing, you know, like one of the issues we've run into with, say, HBase is you doing a lot of very uniform writes. You get into you know, compaction storms or split storms and stuff like that. And are you know, given all this emphasis on making it easy to do, I'm assuming that you're handling that some way. I'm just wondering if that's
so the GC layer is kind of separated from the shard layer,
okay.
And there is opportunity to sort of make them work together, but it's architecturally very hard because it's a big code base, right? And then if you start merging these things, it just becomes a maintenance hell. Because it's different people that know different parts and things like that. So they're sort of independent from each other. The sharding does happen automatically. I think if you start doing, I mean, we've tested uniform writes and things like that, and we haven't encountered very many problems. But again, it's on a scale of 16 shards.
Right.
If you have 200 shards, I don't really know what's going to happen. I mean, there's probably going to be bottlenecks like that. But the resharding is actually pretty good in the sense that it copies the minimum possible amount of data. So it's pretty efficient.
And are you're using, at least if you're, I guess if you're allowing the dirty reads, then you have the possibility of keeping things online.
Well, dirty reads are optional, right? You can turn them on if you want.
Right.
Yeah, so if you're doing dirty reads, you can keep the whole thing online. The availability during resharding is kind of tricky.
Yeah.
It happens, so right now, depending on how things are laid out, you'll get availability while you reshard about 50% of the time. And we could actually get it to 100% of the time, but there is like work, right, to make that.
Work.
Yeah, I know.
Yeah.
It's
yeah.
So that could be done. I don't know when, but it's sort of important to a lot of people, especially if you're running like.
Yeah.
I mean, the web service, you can't be done. If it's an analytics thing, it's different. But for a real-time system, it's very important.
Is there some kind of, do you support, client support multi-tenancy? Like if you have multiple users, any quota system or this thing so that?
That is something that we've considered, but we don't support right now.
We actually have a quota system internally for all sorts of things. Like the garbage collector has its own quota, but it's not exposed. Again, it's work, right? But it could be at some point. We thought about it. I don't think it's pretty high on the priority list, but it will happen.
Okay. Any other questions, or are we good?
Deal.
All right. Thank you. And thank you all for paying attention to us. I hope you found this enlightening.